This is CPE 133, and we're in Chapter 16 in 3-range Verilog Foundation Modeling Text. This is the chapter on test benches, and essentially this means verification. So you're checking to see if your circuit works or not. So this is Part A, multi-part lectures. There's the standard disclaimer. To learn Verilog, you actually have to do it. And so this is actually super important in the realm of verification because it's a totally different animal. And so as you'll see as we come up here, so well, let's just go. Digital design, that's a two-step process. Now look, I mean, it's design and verification. Verification is you're testing to see if your design works. Now in the real world, it may be you testing your design, or it may be some other entity testing your design. There's arguments for both. So there's two different worlds, and for design, we're making sure our design synthesizes, which means, you know, something that's actually realizable in actual hardware. Verification, it's not being synthesized, so it's a different mindset, and it's essentially it's kind of software looking, and like I said, it's completely different. Verification, it's definitely the harder part of the design. Now the issue here is if you have a little simple circuit like, you know, half adder, you could actually test every possible input and check the outputs, verify it's working properly. But when you get a huge circuit, it becomes absolutely impossible to test every single input. You know, particularly if you have a circuit with 20 inputs, right? You know, right there you're at, you know, 2 to the 20th. You got a lot of inputs. It's going to take a long time. You don't do it. And so it's really tough to verify a circuit for a couple of reasons. So, you know, you have to decide first if the amount you're testing is enough to prove your design works. So essentially, once again, you need to test that. You need to understand the design to design the tests for the design. And the issue here, generally speaking, is that you understand the design well enough to generate a small subset of testing that will, I don't know, test enough of the circuit to allow you to say, hey, it actually works. The other issue here is, you know, your boss is going to want you to say, hey, your design works, and essentially once you say that, you're responsible for the errors in your design if you claim that it works. So testing, super important. It's really tough, and more on that in a second. So this course is a beginning course in digital design. Typically speaking, we are visually testing most of our designs. Now the issue, but not all of them. Okay, the issue is the designs that we're doing in this class are pretty easy, and they're actually easy to test visually. But the issue is we got to give you testing skills for the next course. Next course requires that you know, test a pretty complex circuit, and you need to know how to work the simulator, the ins and outs of it. You need to get into that mode of thinking to you know, write the test vectors such that it generates all the right stuff, and you think, hey, my circuit works. So keep in mind that this course, we're taking a very limited approach to verifying our circuits work. We're putting more effort into we'll say the design end of it. The justification here is it's a design course. There's not that much time. Verification is kind of the afterthought in this one, unfortunately. So one of the issues here is there's many tools in Verilog that we're not going to use essentially for the verification process, and there's even a whole bunch more tools in System Verilog that we absolutely don't get there. So there's two types of testing out there. There's behavioral testing and functional testing. So behavioral testing is simply testing whether the logic in your design works. Now what that means is it's different than functional testing because it's ignoring all the properties typically associated with a digital circuit, like prop delays and delays and lines and clock skew and all these fun things. It's just seeing if your circuit works in an ideal setting. Now the issue here is you can actually view this as a two-step process. Well, I'm going to get my design to work behaviorally, and then I'm going to move over to a functional testing. And essentially, that's testing of the synthesized circuit, and you'll see, particularly in Vivado, there's all sorts of different testings. The idea is when you drop this on an FPGA, it has all sorts of routing issues, and it's placed in route automatically for you. It does the best it can, but there are going to be issues with it, particularly as you bump the clock speed up of your circuit. So the approach that we're going to take for verification is to give your circuit some inputs over a given amount of time, and then you're going to do something with the outputs of that. Now, essentially, one of the things you can do is visually inspect those outputs, like in a timing diagram. You could actually write into your test bench some automatic inspection tools or constructs, or you can actually spit out the data to an external file and verify it externally. So a whole bunch of options here. Generally speaking, we're just going to generate a timing diagram and look at it and say, oh, it works, and that's going to work for us essentially because, once again, the circuits are relatively simple. It gets more complicated. By all means, you're going to automate the testing. It's going to be done with computer. You're going to have a different set of software generate the test vectors and the expected results, and you're going to compare them with, we'll say, either the behavioral or functional simulation. So testing, verification is just a whole different animal all of its own. And like I said, we're not going to get to a lot of those issues. So this is a simple test bench model, and it has generally two blocks in there. One's the stimulus driver, and one's the design under test. I always call it device under test, but it's the design under test. So this is the design under test. The idea here is I am going to send it. The stimulus driver is going to send it some test vectors, and the design under test is going to generate some outputs, which I may go to the outside world here, or I could actually send some outputs back to the stimulus driver and have the stimulus driver do something with those outputs. A couple different ways to do it. Generally speaking, we are only going to send it to the output here, at least in this course. So this is a really complicated test bench structure, which you'll run into in real life. So it still has a stimulus driver and a device under test, and most of it's the same, but you can do a couple different things. You can read test vectors from the outside world. The stimulus driver can do stuff with those kind of in a control manner, and I can actually I could read expected results from the file also and make a comparison. I can actually take those results, spit them out to a file, compare them separately, or just have a note saying, hey, it worked or it didn't work. Really intensely complicated stuff. You can do amazing things with it. That Verilog provides tools to do that, but pretty much we're not going to do that. We're only going to, once again, survive on these two boxes. So there's a couple different ways, a couple different constructs to support our notion of verification, and one is a new procedural block. There are two types of procedural blocks. We've worked extensively with always blocks, but now we are at the initial block. Now, initial block is very special because here it's particularly is non-synthesizable, and what that means to you is that it's used specifically for verification. So what happens is the simulator evaluates that initial block one time, and it starts at time 0. So these there's some other stuff that'll make more sense when we get to it. So the issue here is the syntax for the initial block looks kind of like an always block, but particularly there's no sensitivity list, which makes sense because it's only runs once. It runs automatically when the simulation starts at time 0. So time in the simulation is handled by the stimulus driver, and generally what it does is it signs some inputs, it waits, it signs some inputs, it waits, etc., etc. So essentially there's a way to specify delay elements, and essentially just a pound sign with a value. So the issue here is it defines time units. Now, anytime in a simulation, the actual test bench itself will define exactly what those time units are, whether it be like nanoseconds or microseconds, etc., etc. But that's something we generally don't do. The tools kind of do that for us. If you need to change it, it's pretty easy to change. It's essentially like a line in the model. So there are the delay elements. The other thing is there's this notion, this keyword of a finish. So that essentially it's a message from your test bench to the simulator that, hey, you're done simulating. You're going to stop your simulation. So the best way to look at this is do an example. And so let's do it. This is just provide a Verilog model and a test bench for 2 input AND gate. So here we go. This is the modified version of our general model. Here's our stimulus driver. Here's our device under test. So the stimulus driver is providing 2 inputs, which is A and B. It's 2 input AND gate, and the output is going to be an X. We used small letters on the inside and capital letters on the outside. Not a big deal how that works. You can do many different ways. You just have to make sure it works. So we'll look at this example here. And so here's our simple AND gate right here. The inside of this thing, as you can see, is specified as lowercase letters here. And what I'm going to do in this test bench is, first of all, this test bench, like, it has no inputs and outputs. There's nothing breaking that dotted line. So what we have here is an empty interface. There's no external signals on it. Only thing there are internal signals, and here they are. Now the initial block is a procedural block, which means the outputs that we're assigning in it have to be registers because it's a procedural block. Yeah, output here can be of wire type. So there's simply get our design ready to go. The next thing we want to do is instantiate the design under test. This is just a normal instantiation, as you know it and love it. The issue here is that we changed the case on these signals. Not a big deal. We could actually use the same case and it would match up fantastically. So there's the instantiation of the device under test. Here's your initial block. There's one initial block, and what this is doing is saying, hey, starts at time 0, and the first thing it does is wait. It waits 10 time units, then it assigns a 1 to A. Waits 10 more sign units, it assigns a 0 to B. Waits 20 more sign units, it assigns B to 1. It waits 30 time units, and then it finishes. So this is kind of not too exciting without a timing diagram. Okay, so here we go. It waits 10 time units. Here's your 10 time units. At that point, A is an unknown. B is an unknown also. Essentially, the inputs are unknown until you assign them. So right here, it gets assigned a 1. Right here, it gets assigned a 0. It waits 20 nanoseconds right here, and then it assigns B a 1, which is right there. And then I wait another 30 nanoseconds, and this is the 30 nanoseconds right there. But what happens is the output right here becomes a 1 when both the inputs are 1, since it is an AND gate. So you can see right there that the input goes high and it stays high until I change it, but I didn't change it. I waited 30 time units, and then I stopped the simulation. And that's about it. It's that straightforward. And so this is an example of a 4-bit comparator. This is a model we used before. I just want to test it just for the heck of it. So let's go look at this thing. I'm not going to get in depth as we did last time, but let's go. Here's your empty external interface. Here are your 2 internal interfaces, such as your signals here. We got 2 inputs which are going to be assigned from the initial block. they need to be declared as regs. Here are your 3 outputs, which is just equal, less than, greater than. Here's your instantiation. I made it a horizontal just to save space so I can fit everything in there, but here we go. So this is the first assignment. It happens at time 0 because I don't see a delay there. What I've used here is hex notation. So it's 4 bits long, it's using hex, and I'm assigning it the value of A, which is 1010, B is 1011, etc., etc. So at this time, at time 20 nanoseconds, I'm sorry, 20 time units later, I'm going to assign A a different value, and I reassign B just for the heck of it, not a big deal. 20 more nanoseconds and I change it just to make it interesting. I am now using binary notation. Notice that it's 4 tick B, B for binary, and I have to assign 4 binary digits on this. 4 bits. And so I wait another 20 nanoseconds and I assign some other values. The values don't make any, they're just arbitrary. I don't have an output timing diagram for this one. And only thing of interest here is I did not put a $ finish in here. Yeah, since I did not do that, it's going to rely on the simulator to stop the simulation for me. Essentially, the simulator piece of software, it always has ability to determine the length of the simulation. So that's it. We're going to continue this in part B. I didn't mean to make this so long, but part B will be shorter.